Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by the right triangle ABC. And in the second question, we'll find out the area of the blue right triangle DCB that is inscribed by the quarter circle AOB. So we'll start with the first question. In the drawing, we have the right triangle ABC, side AB equals to 8 units. We also know that side BC and side AC, or the lengths of side BC and side AC, are integers. And we want to find out the radius of this circle that is inscribed by the right triangle ABC. So first of all, we'll define side BC as A. Side BC equals to A, it's according to our definition. And we define the hypotenuse AC. Side AC is equal to B units. Okay. In the next step, we'll implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, in the right triangle ABC, by PT is a relation from Pythagoras theorem. The hypotenuse is AC, so the square of the hypotenuse is AC squared. And it is equal to BC squared plus AB squared. I'll repeat again. In the right triangle ABC, AC squared equals to BC squared plus AB squared. Okay. AC equals to B according to our definition, therefore AC squared is B squared. It is equal to BC squared. BC equals to A according to our definition, so BC equals to A squared plus AB squared. AB equals to 8, so AB squared is 8 squared, that is 64. So we find out that B squared equals to A squared plus 64. Okay. Here we subtract A squared from this equation, and we get that according to equation number 1, B squared minus A squared equals to 64. According to the algebraic identity, B squared minus A squared equals to B plus A times B minus A. So we substitute B squared minus A squared by B plus A times B minus A. And it is equal to 64 according to equation number 1. According to what is given as the question, BC and AC are integers. So that is to say BC is A and AC is B, so A and B are integers. And AC and BC actually A and B are the lengths of the sides of the right triangle ABC. So A and B as the lengths, they must be positive numbers. They are lengths, therefore they must be positive numbers. So from those two things we derive that A and B must be positive integers. A and B are positive integers. So A is a positive integer and B is a positive integer, so B plus A, when you add two positive integers to each other, the result must be a positive integer. But B plus A must be greater than B minus A. Because when you add two positive integers together, the result must be greater than the situation that when you subtract one from the other. Okay, so B plus A must be greater than B minus A. According to what is given us in the question, so according to our definition, B is the hypotenuse, and the hypotenuse is always greater than the perpendicular, so we know that B is greater than A. If we subtract A from this inequality, we get that B minus A is greater than 0, that is to say, B minus A is a positive number. So B is a positive integer, A is a positive integer also, so when you subtract two positive integers from each other, if the result is positive, it means that the result must be also a positive integer. So B minus A is also a positive integer. So actually, we have here information that when we multiply two positive integers by each other, that is to say, B plus A times B minus A, the result is 64. So which two positive integers we have that when we multiply them by each other, the result will give us 64. There are not a lot of possibilities here. It might be 1 and 64. 1 times 64 is 64. It might be 2 and 32. 2 times 32 is 64. It might be 4 and 16. 4 times 16 is 64. It might be 8 and 8. 8 times 8 is also 64. It might be 16 and 4. 16 plus 4 is also 64. it might be 32 times 2, that is also 64. And the last possibility is that the two numbers are 64 and 1, because 64 times 1 is also 64. Okay, so we have here 7 possibilities for the solution to the question. So, but because of the fact that we only found out that b plus a must be greater than b minus a, it means that this column must be greater, the first column must be greater than the second column. According to what we already found out, b plus a must be greater than b minus a, so the first column must be greater than the second column. Okay, so 1 is not greater than 64, therefore this solution is incorrect solution. 2 is not greater than 32, therefore it is not correct solution. 4 is not greater than 16, it is not a correct solution. 8 is not greater than 8, it is not a correct solution. 16 is greater than 4, it is a good solution. 32 is greater than 2, it is a good solution, and 64 is also greater than 1, therefore it is also a good solution. In the next step, we will add the two numbers together in order to find out what is the result of adding the two numbers together. So here, b plus a plus b minus a, if we add equation number 1 to equation number 2, we get that b plus a is 2b and a minus a is 0. So in conclusion, if we add the two numbers together, we get 2b, that is it is an even number. Because b is a positive integer, 2 times b must be an even number. It means that if we add the two numbers together, the result must be an even number. That is to say, if we get an odd number, it is not a good solution. We'll cancel the solution. So we'll find out here in which cases, when we add the two numbers together, we'll get an even number. 16 plus 4 is 20. 20 is an even number, so it is a good solution. 22 plus 2 is 34, that is an even number, therefore it is a good solution. But 64 plus 1 is not it is 65, that is not an even number, but it is an odd number, so we cancel the solution. We left only with two solutions that are possible. Either b plus a is 16 and b minus a is 4, or the second solution is that b plus a is 32 and b minus a is 2. So we write down the two solutions that are possible for the question. The first solution is that b plus a is 16 and b minus a is 4. This is the first solution. And the second solution to the question is that b plus a is 32 and b minus a is 2. So in the next step we'll find out the values of a and b in each solution. So here we add the first equation to the second equation, and we get that b plus b is 2b, a minus a is 0, so 2b equals to 16 plus 4 is 20. We found out that 2b equals to 20. Here we'll divide this equation by 2, and we'll get that 20 over 2 is 10, so found out that b equals to 10 units. And we also know that b plus a is 16. So we subtract b from this equation and we'll find out that a equals to 16 minus b, that is to say a equals to 16 minus b, and b is 10, so it is 16 minus 10, that is 6. So according to the first solution, I found out that a equals to 6 units and the hypotenuse b equals to 10 units and the perpendicular a equals to 6 units. And according to the second solution, we get that if we add the two equations together, b plus b is 2b, a minus a is 0, so 2b equals to 32 plus 2 is 34. Here we divide this equation by 2, and we get that b equals to 34 over 2 is 17. b equals to 17 units. And we already found out that b plus a is 32. Here we subtract b from this equation and we get that a equals to 32 minus b. So a equals to 32 and we already found out that b equals to 17, so we substitute b by 17, so it is 32 minus 17, that is 15. So according to the second solution, we found out that a equals to 15, a, that is the perpendicular of the right triangle ABC, is 15 units, and the hypotenuse b equals to 17 units. Okay, so here we will draw, in the next step we will draw the two solutions. Here, according to the first solution, we actually have here a right triangle. In this right triangle, triangle ABC, it is given us in the question that AB equals to 8 units. We just right now found out that BC, that is A, equals to 6 units, and the hypotenuse AC, that is B, equals to 10 units. And according to what is given as the question, inside this right triangle, triangle ABC, we have a circle that is inscribed by the triangle ABC. And we actually want to find out the radius of this circle that is inscribed by triangle ABC. So we define the radius as R, capital R, and the center of the circle is O. We want to find out the radius of this circle that is inscribed by this triangle, triangle ABC. This is the first possibility, the first solution to the question. And according to the second solution, we found out that the hypotenuse A equals to 15 units. This is our triangle ABC. It is given us the question that side AB equals to 8 units. We have just right now found out that BC, that is A, equals to 15 units, and the hypotenuse AC equals to 17 units. Inside this circle, we have, inside this triangle, inside this right triangle, we have a circle that is inscribed by this right triangle. And we actually want to find out the radius of this circle, that is to say the value of R. Here the center of the circle is point O. So we want to find out the radius of this circle that is inscribed by the right triangle, this right specific triangle, triangle ABC. So we have two possibilities for the answer for the radius. So in the next step, we will find out a general formula for the radius of any circle that is described by a right triangle. So we will draw a right triangle, triangle ABC, that could be any triangle. Okay. So this is the right triangle, triangle ABC, that could be any triangle. Inside this right triangle, triangle ABC, we have this circle, and we want to find out the radius of this circle that is described by the right triangle, triangle ABC, that could be any triangle. So here, we know that side AB is equal to A units according to our definition. Side BC equals to B units according to our definition. And side AC, the hypotenuse of the right triangle ABC, equals to C units according to our definition. Okay. So the center of this circle is at point O. We will define the point of tendency of tangent BC with this circle SM. We will define the point of tendency of tangent AB with this circle SM. We will join points O and N together by a straight line. So what is the definition of line segment ON? This line segment, O is the center of the circle, N is the point of the circle itself. This is exactly the definition of a radius. So ON equals to the radius of the circle, that is capital R according to our definition. So here we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO according to rule number 1, it means that this angle equals to 90 degrees, and this angle will also equal to 90 degrees. Likewise, we have here the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equal to 90 degrees according to rule number 1. So inside quadrilateral NOBM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So actually 270 degrees plus the size of the fourth angle, that is actually angle NOM. This angle, in total, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is 360 degrees. That is to say, the missing angle, angle NOM, must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral NOBM to 360 degrees. This angle must be equal to 90 degrees. So actually found out that in quadrilateral, side quadrilateral NOBM, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. But we have already found out that NO equals to R from one side, and from the other side, NO equals to BM. That is to say, BM also equals to R. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. From one side, OM equals to NB. But from the other side, we have already found out that OM equals to R. Therefore, NB that is equal to OM must be also equal to R. So we actually found out that for the other NOBM, it is not a rectangle but a square. Because all of its sides are equal to each other, they are equal to R. In the next step, we found out the length of line segment AN. Here, AN, you can see it is very easy to see from the drawing that AN equals to AB minus NB. Again, AB minus NB equals to AN. That is to say, AN equals to AB, that is A, minus NB, that is R. So in conclusion, we found out that AN equals to A minus R. In the next step, we will find out the length of line segment MC. From the drawing, it is very easy to see that MC equals to BC minus BM. Again, BC minus BM equals to BC. That is to say, MC equals to BC, that is B, minus BM, that is R. So in conclusion, we found out that MC equals to B minus R. Then we actually have rule number 2, that the lengths of two tangents from a common external point to a circle are equal. And repeat again, the lengths of two tangents from a common external point to a circle are equal. So if we focus on the common external point, point A, from point A we have two tangents to this circle, tangent AN and tangent, here we define the point of tangency of tangent AC with this circle as L. So from point A we have two tangents to this circle, tangent AN and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AN equals to AL according to rule number 2. But we have already found out that AN equals to A minus R. Therefore, AL that is equal to AN must be also equal to A minus R. Okay. Likewise, if you focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle, tangent CL and tangent CM, and according to rule number 2, they are equal to each other. So CM equals to CL according to rule number 2, but we have already found out that CM equals to B minus R. Therefore, CL that is equal to MC must be also equal to B minus R. Here, CL equals to B minus R. So in conclusion, we found out that CL equals to B minus LC equals to B minus R, and AL equals to A minus R. So what is the length of the hypotenuse AC? Actually, the length of the hypotenuse AC, it is equal to AC. From the drawing, it is very easy to see that AC equals to AL plus LC. AL plus LC. I repeat again, the hypotenuse AC of the right triangle ABC equals to AL plus LC. AC equals to C according to our definition, so we substitute AC by C. AL, this is AL that is equal to A minus R, according to what we have already found out. Plus LC, we have already found out that LC equals to B minus R. So in conclusion, we found out that the hypotenuse C equals to A minus R plus B minus R. That is to say, the hypotenuse C equals to A plus B minus R is minus 2R. Here we add 2 out of this equation and we get that C plus 2R equals to A plus B here we'll subtract 3 from this equation, and we get that 2r equals to a plus b minus c. Here we'll divide this equation by 2, and we'll get that r equals to a plus b minus c over 2. So we found out the general formula for the radius of any circle that is described by a right triangle ABC, that will be any triangle. That is to say, we can implement the new formula in our two triangles. According to the new formula, r equals to a plus b minus c over 2. That is to say, it is equal to the sum of its perpendiculars minus the hypotenuse over 2. So in this specific triangle, the radius of this circle will be equal to, according to this formula, to a plus b, that is 8 plus 6, that is 14, minus c, that is 10, over 2. 14 minus 2 is 4, and 4 over 2 is 2. So we found out that the radius of this circle equals to 2 units, according to this formula. In the next step, we'll find out the radius of this circle in the right triangle ABC. So here the radius will be equal to a plus b, that is 8 plus 15, minus AC, that is 17, over 2. 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So here we found out that the radius equals to 3 units. R equals to 3 units. So actually we have two solutions to this question. The first solution to this question is that the radius of this circle, as is described by the right triangle ABC, equals to 2 units, and according to the second solution, the radius of this circle that is described by the right triangle ABC equals to 3 units. And that is the answer to the question. R equals to either 2 units or 3 units. We finished with the first question. In the next step, we'll present to you the second question, and we'll solve the second question in 2 different methods. Okay. In the drawing, we have a quarter circle A or B is a quarter circle, side OB equals to 2 units, AD equals to DO, according to what is given in the question. Inside this quarter circle, we have the right triangle, the right blue triangle, triangle DCB, angle VCD equals to 90 degrees, and we want to find out the area of this right triangle, right blue triangle, triangle VCD. So first, we'll start with the first method. Here, in any quarter circle, A or B equals to 90 degrees. Angle A or B equals to 90 degrees. And the radius of this quarter circle is OB, that is 2 units. And the radius is also AO, that is also 2 units. Okay? So we can write here that AO is also equal to 2 units. This is the radius of the quarter circle. And we know that AD equals to DO. So we can write down that AO equals to OB. AO equals to OB equals to the radius of the quarter circle, that is equal to 2 units. And we also know from the drawing that AO equals to AD plus DO. AO equals to AD plus DO. AD equals to DO, so if we define AD as X, then DO will be also equal to X. So AD equals to x and DO equals to x. That is to say, x plus x is 2x, and 2x equals to 2. We divide this equation by 2, and we get that x equals to 1 units. So here, AD that is equal to x equals to 1 unit, and DO that is also equals to x, it is also equals to 1 unit. So, in the next step, we'll complete the quarter circle to a circle. And we completed the quarter circle to a circle. We'll extend the radius BO by a straight line until it touches the circle. Here we define the touching point of the extended BO with the circle as point P. O is the center of the circle, as I already mentioned. O is the center of the circle, and P is the point of the circle itself. Therefore, PO is the radius of this circle that is equal to 2 units according to what is given as the question, because the radius of the circle is also the radius of the quarter circle. Okay. In the next step, we will extend side CD by a straight line until it touches the circle. So, at which point the extended CD will touch the circle. We don't know at which point, so we will assume that the extended side CD will touch the circle at this point. This is actually point X. Okay? So we actually created here peripheral angle BCX. I write it down. We have the peripheral angle BCX. Angle BCX is the peripheral angle and according to what is given as the question, peripheral angle BCX equals to 90 degrees. Okay? But because of the fact that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, it means that peripheral angle BCX must rest on PB, that is the diameter of the circle. PB is the diameter of the circle because of the fact that it passes from the center of the circle, that is point O. So, peripheral angle BCX that is equal to 90 degrees must rest on the diameter of the circle, that is PB. Therefore, points X and P must merge with each other, or it is point X must merge with point P in order that peripheral angle BCX that is equal to 90 degrees will rest on the diameter that is PB. That is to say, we will get here the straight line CD. When we extend the side CD by a straight line, it must touch the circle only at point P, only and only at point P, and not in any other point. In order that peripheral angle BCP will be equal to 90 degrees, in order that peripheral angle BCP that is equal to 90 degrees will rest on the diameter that is PB. It means that the straight line CD, when we extend it, it must touch the circle at point P and only at point P. Otherwise, the peripheral angle BCX will not rest on the diameter that is PB. That is to say, peripheral angle BCX is actually equal to peripheral angle BCP. Okay? So here you can write down that peripheral angle BCX equals to peripheral angle BCP because it must rest on the diameter of the circle that is BP. Okay? Here PB, it is the diameter of the circle, therefore it is absolutely a straight line. And we know that the sum of the angles on one side of a straight line equals to 180 degrees, so if we focus on the upper side of the straight line PB at point O, the sum of the angles here must be equal to 180 degrees. So this angle equals to 90 degrees, plus this angle that is actually angle AOP, total they must be equal to 180 degrees. That is to say, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles here to 180 degrees, this angle AOP must be equal to 90 degrees. So this angle equals to 90 degrees. In the next step, we will implement the Pythagoras theorem on the right triangle POD. In the right triangle POD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle POD, by PT, a version for Pythagoras theorem, PD squared equals to d whole square plus p whole square. I repeat again, in the right triangle POD, PD square must be equal to d whole square plus p whole square according to the Pythagoras theorem. So PD square, that is the square of the hypotenuse, must be equal to d whole square. D whole is 1, so d whole square is 1 square, that is 1, plus p whole square. P whole equals to 2, so p whole square is 2 square, that is 4. So in conclusion, we found out that PD square equals to 1 plus 4, that is 5. We will take out of this equation, we will get that PD equals to the square root of 5 units. PD equals to the square root of 5 units. We repeat on the same process on the right triangle DOB, the right triangle DOB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB square must be equal to d whole square plus OB square. Repeat again, dB square must be equal to d whole square plus dB square. So dB square must be equal to d whole square. Here d whole equals to 1, so d whole square is 1 square, that is 1, plus dB square plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, we found out that dB squared equals to 1 plus 4, that is 5. We'll take out of this equation, and you will get that dB equals to the square root of 5 units also. So here dB equals to the square root of 5 units. We'll extend line segment AO by straight line until it touches the circle. At this point, we will define the touching point of the extended AO and the circle as point Q. In the next step, I present to you rule number 1 that is related to two chords that intersect with each other inside the circle. So we have this circle, and here we have chord AB. This is chord AB. That intersects with chord CD. This is chord CD. At point O. So if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Okay. AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AQ. Chord AQ intersects with chord CP at point D. I will write it down. Chord AQ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DQ equals to PD times DC. I repeat again. Chord AQ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DQ equals to PD times DC. Again, AD times DQ equals to PD times DC. According to rule number 1, AD equals to 1, DQ equals to here. What is the length of OQ? O is the center of the circle, Q is the point of the circle itself. That is to say, this is exactly the definition of a radius. OQ is the radius of the circle, that is equal to 2 units according to what is given as the question. So what is the length of DQ? DQ equals to 1 plus 2, that is 3. DQ equals to 3 units. PD equals to square root of 5 units times DC. DC is the missing 9 segment. So found out that 3 equals to square root of 5 times DC. So DC equals to, we divide this equation by square root of 5, and we get that DC equals to 3 over square root of 5 units. So we can write here that DC equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. On the right blue triangle, triangle DCB, according to the Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, dB square equals to DC square plus CB square. I repeat again, according to the Pythagoras theorem on the right blue triangle, triangle DCB, dB square equals to DC square plus CB square. dB equals to square root of 5 units, so dB square is square root of 5 square, that is 5, it is equal to DC square. DC is 3 over square root of 5, so DC square is 9 over 5, plus CB square. CB is the missing 9 segment, so we leave it as it is. Here we subtract 9 over 5 from this equation, and we get that 5 minus 9 over 5 equals to CB square. Here we multiply 5 by 5 and then we divide it by 5 in order to have a common factor of this expression. 5 times 5 is 25, minus 9 over 5 equals to CB square. Here 25 minus 9 is 16, so 16 over 5 equals to CB square. Here we take out of this equation and we get that CB equals to the square root of 16, it is 4 over square root of 5. So now that CB equals to 4 over square root of 5, CB equals to 4 over square root of 5. Now it is very easy to find out the area of the blue white triangle, triangle DCB. The area of triangle DCB will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. I repeat again, the area of triangle DCB equals to the base of the triangle, that is DC or CD, times the height to the base, that is CB, over 2. So DC or CD is 3 over square root of 5 units, times CB, CB is 4 over square root of 5 units, all divided by 2. Here 3 times 4 is 12, square root of 5 times square root of 5 is 5, times 2. 12 over 2 is 6, in the denominator we left only with 5. So found out that the area of the right blue triangle, triangle DCB, equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, so I'm finished with the first method. The next step we present to the second method. So we have already found out that this angle equals to 90 degrees. In the first method, AD equals to 1 unit, DO equals to 1 unit. In the next step, we complete the quarter circle to a semicircle. We'll extend the radius BO by a straight line until it touches the circle at point P. Point O is the center of the circle, point P is the point on the circle itself, therefore PO is the radius of this semicircle that is equal to 2 units according to what is given as the question. We'll extend side CD by a straight line. According to the first method, when we extend the straight line CD, the side CD by a straight line, it must touch point P, it must pass for point P. So this will be here angle BCP is equal to 90 degrees. So according to the first method, this angle equals to 90 degrees. We define, and according to the first method, PD equals to the square root of 5 units, and DB also equals to the square root of 5 units. We define angle DPO as theta. In the right angle DPO, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles of the right angle DPO to 180 degrees, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Okay, we'll focus on the right angle CPB. This angle equals to theta, this angle equals to 90 degrees, so this angle must be also equal to 90 degrees minus theta. For the same reason that this angle also equals to 90 degrees minus theta. In the next step, we will prove that the right triangle POD is similar to the right big triangle BCB. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle POD, this angle equals to this angle that is actually angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. I'll repeat again. Angle POD equals to angle PCB equals to 90 degrees. In addition, this is a common angle that belongs to both triangles, so this angle equals to itself. So angle DPO equals to angle CPB, and it is equal to theta. It is a common angle that belongs to both triangles. And finally, those two angles are equal to 90 degrees minus theta, therefore they are equal to each other. So this angle PDO equals to this angle that is actually CBP, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. Okay, I repeat again, angle PDO equals to angle CBP, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So we found out that all three angles on the right triangle POD can go into all three angles on the right triangle PCB, therefore triangle POD is similar. This is the sign of similar to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB, and it is equal to PO over PC. Repeat again, we conclude that PD over PB equals to DO over CB equals to PO over PC. So if PD is equal to 5 units over PB is 2 plus 2, that is 4, DO is 1, CB is the missing line segment, so we leave it as it is, and it is equal to PO is 2 over PC is equal to 5 plus DC. So in conclusion, we found out that it's equal to 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. We will derive the first equation from this long equation, that square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation number 1, and we get that according to equation number 1, square root of 5 times CB equals to 4. Here we divide this equation number 1 by square root of 5. And we get that according to equation number 1, CB equals to 4 over square root of 5 units. CB equals to 4 over square root of 5 units. Here, CB equals to 4 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. In the right blue triangle, triangle DCB, according to the Pythagoras theorem, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, dB squared equals to DC squared plus CB squared. So dB squared equals to DC squared, that is the missing line segment, plus CB squared. CB is 4 over square root of 5, so CB squared is 16 over 5. So if I know that dB squared equals to DC squared plus 16 over 5, dB is square root of 5, so dB squared is 5. So we found out that 5 equals to DC squared plus 16 over 5. Here we subtract 16 over 5 from this equation, and we get that 5 minus 16 over 5 equals to DC squared. Here we multiply 5 by 5 and then we divide it by 5 in order to become comfortable with this expression. 5 times 5 is 25, so 25 minus 16 over 5 equals to DC squared. So 25 minus 16 is 9, and 9 over 5 equals to DC squared. We take out of this equation and we find out that DC equals to the square root of 9, that is 3, over square root of 5. So we found out in conclusion that DC equals to 3 over square root of 5. Now it is very easy to find out the area of the blue white triangle, triangle DCB, the area of the blue white triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. Repeat again, the area of the right blue triangle, triangle DCB equals to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. DC equals to 3 over square root of 5 units, CB equals to 4 over square root of 5 units, all divided by 2. So here in the numerator we have 3 times 4 is 12. In the numerator we have square root of 5 times square root of 5 is 5, times 2. And 12 over 2 is 6, and the denominator we left only with 5. So from all the area of the light blue triangle DCB equals to either 6 over 5 units, or in terms of numbers it is equal to 1.2 square units. Okay. So in the next step, I will summarize the lecture. We start with the first question. So in the drawing, we have a right triangle, triangle ABC, side AB equals to 8 units, side BC and side AC are integers. Angle ABC equals to 90 degrees. Inside this right triangle we have a circle that is inscribed by triangle ABC, and we want to find out the radius of this circle that is inscribed by the right triangle, triangle ABC. So first of all, we define side BC as A and side AC the hypotenuse as B, and we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, AC squared equals to BC squared plus AB squared. AC is B, so AC squared is B squared. BC is A, so BC squared is A squared. AB is 8, so AB squared is 8 squared, that is 64. We subtracted A squared from this equation and found out that B squared minus A squared equals to 64. We used the trigonometric algebraic identity that B squared minus A squared equals to B minus A times B b plus a times b minus a. Okay, and it is equal to 64 according to equation number 1. So actually note that according to what is given in the question, BC and AC are integers. BC equals to A and AC equals to B, so A and B are integers. And we also know that A and B are the lengths of the right triangle, triangle CB, therefore there must be positive numbers. So from those two things we derive that A and B are positive integers. Okay? And because of the fact that A and B are positive integers, it means that B plus A must be greater than B minus A, because when you add two positive integers to each other, the result must be greater than the situation when you subtract them from each other. So B plus A must be greater than B minus A. B is positive integer, A is positive integer, therefore B plus A must be also a positive integer. And we know that the hypotenuse is greater than the perpendicular in a right triangle, therefore B is greater than A. We subtracted A from this equation, and we got that B minus A equals to 0. That is to say, B minus A is a positive number. B is a positive integer, A is a positive integer, and this B minus A is a positive. That is to say, B minus A must be also a positive integer, because when you subtract or add positive integers to other positive integers, the result also always will be positive integer. Okay, so if the result here is not a negative number, then the result of B minus A, that both of them are positive integer, must be a positive integer. So B minus A, it is also a positive integer, and B plus A, it is also a positive integer. So we have here, according to equation number 1, we multiplied two positive integers by each other, and the result is 64. What are all the possibilities that when you multiply two positive integers with each other, the result will be 64? There are a lot of possibilities here. Either B plus A is 1 and B minus A is 64. Either B plus A is 2 and B minus A is 32. Either B plus A is 4 and B minus A is 16. Or B plus A is 8 and B minus A is 8. B plus A is 16 and B minus A is 4. B plus A is 32 and B minus A is 2. And the last option is that B plus A is 64 and B minus A is 1. So we have 7 possibilities to multiply two positive integers by each other, and the result will be 64. We have only 7 possibilities, but because of the fact that B plus A is greater than B minus A, it means that the first column must be greater than the second column. If 1 is not greater than 64, this is not a good option. 2 is not greater than 32, it is not a good option. 4 is not greater than 16, it is not a good option. 8 is not greater than 8, it is not a good option. 16 is greater than 4, it is a good option. 32 is greater than 2, that is a good option. And 64 is greater than 1, it is also a good option. So we have 3 good options for the solution to the question. Now we will add the two numbers together in order to see what is the result. So we added B plus A to B minus A, and we got that B plus B is 2B and A minus A is 0. So in conclusion, when we add the two numbers together, the result is 2B, that is an even number. It means that if we add the two numbers here together, the result must be an even number. So we'll check here which result is an even number. And if we get an odd number, we'll cancel this possibility, because the result must be an even number. So here 16 plus 4 is 20. 20 is an even number, therefore this is a good possibility. 32 plus 2 is 34. That is an even number. This is also a good possibility. And 64 plus 1 is 65. That is an odd number. It is not an even number. Therefore, we cancel this solution and we're left only with those solutions. In the next step, we'll find out the values of A and B in each solution. So according to the first solution, B plus A is 16 and B minus A is 4. And according to the second solution, B plus A is 32 and B minus A is 2. So here in the first solution, we'll add the two equations together. B plus B is 2B, A minus A is 0, and 16 plus 4 is 20. So in conclusion, we found out that 2B equals to 20. We divided this equation by 2 and we got that B equals to 20 over 2, that is 10. So we found out that the hypotenuse B equals to 10 units. Then we have this equation that B plus A equals to 16. We subtracted B from this equation and we found out that A equals to 16 minus B. A equals to 16 minus B. And B equals to 10, so we can substitute B by 10 and we get that A equals to 16 minus 10, that is 6. So we found out that perpendicular A equals to 6 units and the hypotenuse B equals to 10 units and AB equals to 8 units is given us the question. So this is the first possibility. The second possibility for A and B here is we add the two equations together. B plus B is 2B and A minus A is 0 and 32 plus 2 is 34. So 2B equals to 34. We divide this equation by 2 and we get that B equals to 34 over 2, that is 17. So we found out that B equals to 17 and according to this equation B plus A equals to 32. We will subtract B from this equation and we get that A equals to 32 minus B. But we already found out that B equals to 17, so we substitute B by 17 and we get that A equals to 32 minus 17, that is 15. So actually in conclusion we found out that A equals to 15 and B equals to 17. So I drew the two solutions in this side of the page. According to the first solution, AB equals to 8 units, this is given as the question. BC equals to 8, that is 6 units, and AC equals to B, that is 10 units. Inside this right triangle, we have this circle that is inscribed by this right triangle, and we want to find out the radius of this circle. And according to the second solution, AB equals to 8 units, BC, that is A, equals to 15 units, and AC equals to the hypotenuse, that is B, that is equal to 17 units. Inside this right triangle, we have a circle that is inscribed by this triangle ABC, and we want to find out the radius of this circle. So we will develop a special formula to find out the radius of any circle that is inscribed by right triangle ABC. So here we have triangle ABC. That could be any triangle. Inside this right triangle ABC, we have this circle, and we find out the radius of this circle. And by finding the radius of this circle, we will develop a formula that is true for any right triangle. So we'll implement the new formula in our two right triangles. So this is triangle ABC, that could be any triangle. Therefore, side AB equals to A units according to our definition, side BC equals to B units, and side AC equals to C units. Then we define the center of the circle as O. We define the point of tendency of tangent AB with this circle as M. We define the point of tendency of tangent BC with this circle as M. And then I presented to you rule number 1. Here actually we join points O and M together by a straight line. Point O is the center of the circle. Point M is the point of the circle itself. This is exactly the definition of radius. So OM is the radius of this circle, that is equal to capital R. Then I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here the radius OM, it is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent BC with this circle. Whenever we have a radius that is drawn to the point of tendency, then according to rule number 1, tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So actually inside quadrilateral ON and BM we have 1, 2, 3 right angles. The sum of 3 angles is 90 times 3 is 270 degrees, plus the size of the fourth angle that is actually angle NOM. In total they must be equal to 360 degrees. Okay, so actually the missing angle must be equal to 90 degrees in order to complete the sum of the angles in this quadrilateral NOBM to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral NOBM we have 4 right angles. Any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to quadrilateral BM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say NO equals to BM. But NO equals to R, therefore BM is also equals to R. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that NB equals to OM. But NB equals to R, therefore OM also equals to R. So quadrilateral OMBM, it is not a rectangle but a square, because all of its sides are equal to R. We found out the length of line segment AN. From the drawing it is very easy to see that AN equals to AB minus NB. AB is A, NB is R, so in conclusion, A equals to A minus R. Then we found out the length of line segment MC. MC equals to BC minus BM. BC is B and BM is R. So in conclusion, MB equals to B minus R. So in conclusion, we found out that MC equals to B minus R and AN equals to A minus R. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. I repeat again, the lengths of two tangents from a common standpoint to a circle are equal. So if we focus on the common standpoint point A, we have two tangents to this circle, tangent AN and tangent AL. And according to rule number 2, they are equal to each other. AN equals to AL. But we have already found out that AN equals to A minus R. And we know that AL equals to AN, therefore AL also must be equal to A minus R. Likewise, we will focus on the common standpoint point C. From the common standpoint point C, we have two tangents to this circle, tangent CL and tangent CM. And according to rule number 2, they are equal to each other. That is to say, CL equals to CM. But we have already found out that CM equals to B minus R, therefore CL also must be equal to B minus R. So in conclusion, we found out that AL equals to A minus R and LC equals to B minus R. So what is the length of the hypotenuse AC? AC equals to AL plus LC. Here AC equals to AL plus LC. AL equals to A minus R. AL equals to A minus R and LC equals to B minus R. LC equals to B minus R. So in conclusion, we found out that C equals to A minus R plus B minus R. Okay, AC equals to A minus R plus B minus R. But according to our definition, AC equals to C, so we can substitute AC by C. And in conclusion, we found out that C equals to A minus R plus B minus R. So C equals to A plus B minus R is minus 2R. C equals to A plus B minus 2R. We added 2R to this equation and found out that C plus 2R equals to A plus B. We subtracted C from this equation and found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that the radius of the circle that is described by the right triangle ABC equals to A plus B minus C over 2. That is to say, it is the sum of its perpendiculars minus the hypotenuse over 2. So actually we can implement the new formula in our two right triangles, because this is a general formula that is true for any triangle. So our new formula is r equals to a plus b minus c over 2. A plus b is the sum of its perpendiculars, that is 8 plus 6, minus the hypotenuse c is 10. 8 plus 6 is 14, minus 10. 14 minus 10 is 4, and 4 over 2 is 2. So we found out that the radius of this circle that is described by this right triangle, triangle ABC, equals to 2 units. And the second possibility is here r equals to a plus b. A is 8, b is 15, so it is 8 plus 15 minus c, that is 17 over 2. 8 plus 15 is 23, 23 minus 17 is 6, and 6 over 2 is 3. So the second solution is that the radius of this circle that is described by the right triangle, triangle ABC, equals to 3 units. So we have here two solutions to the question. That according to the first solution, the radius equals to 2 units, and according to the second solution, the radius of this circle that is described by the right triangle, this right triangle, triangle ABC, equals to 3 units. We finished with the first question, then I presented to you the second question, and we solved the second question in two different methods. Here in the drawing we have a total circle. The side OB equals to 2 units, AO equals to DO, and inside this quarter circle we have the right triangle, triangle CDB, and we want to find out the area of this right triangle, triangle CDB. So because of the fact that this is a quarter circle, AOB, this angle equals 90 degrees, point O is the center of the quarter circle, and the radius OB equals to 2 units, therefore the radius AO is also the radius that is also equals to 2 units. And here we know that AD equals to DO, and AO equals to AD plus DO. Okay, here AO equals to AD plus DO. So we defined AD as x, then DO must be also equal to x because AD equals to dx. It is equal to OB, it is equal to the radius of the quarter circle, that is 2 units according to what is given as the question. So in conclusion, we found out that x plus x equals to 2. We divided this equation by 2 and we found out that x equals to 1 unit. So here, AD that is x equals to 1 unit, and DO that is also x, it is also equals to 1 unit. Then we completed the quarter circle to a circle, and we extended side BO by a straight line until it touches the circle at point P. O is the center of the circle, P is the point of the circle itself, therefore PO is the radius of the circle, that is 2 units. Chord PB passes through the center of the circle, therefore chord PB is the diameter of the circle. Then we extended side CD by a straight line until it touches the circle. So we don't know where it touched the circle. So we will define that when we extend the straight line CD, we touch the circle at point X, this point. It is not point P. Okay? So we actually created here peripheral angle. Angle BCX is a peripheral angle that is equal to 90 degrees. Here we have the peripheral angle BCX that is equal to 90 degrees. And according to our assumption, peripheral angle BCX not passes through point P. But because of the fact that peripheral angle BCX equals to 90 degrees, it must pass through point C, from point P. Because any peripheral angle that is equal to 90 degrees must rest on the diameter. The diameter is PB, so in order that peripheral angle BCX will rest on the diameter that is PB, it must pass, the straight line CD must pass through point P. Otherwise, peripheral angle BCX will not rest on PB, that is the diameter of the circle. That is to say, point X must merge with point P. That is to say, peripheral angle BCX equals to peripheral angle BCP. Peripheral angle BCX equals to peripheral angle BCP. Otherwise, we will arrive to the contradiction. We'll get peripheral angle that is equal to 90 degrees, and it is not resting on the diameter. This is a contradiction. In order to avoid the contradiction, here the straight line CD must pass from point P, that is to say, peripheral angle BCX equals to peripheral angle BCP, that is to say, point X merged with point P. Okay? Then we have here BP is the diameter of the circle, therefore it is absolutely a straight line. And we know that the sum of the angles on one side of a straight line equals to 180 degrees, therefore this angle must be equal also to 90 degrees. Okay? Then we extended the radius AO by straight line until it touches the circle at point Q. So here point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equal to 2 units. Then we implemented rule number 1 in our drawing. We have here, according to rule number 1, if chord AB intersects with chord CD at point O, it is a chord inside the circle. So if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AQ that intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D, therefore according to rule number 1 we get that AD times DQ equals to CD times dP. Again, AD times dQ equals to CD times dP. AD times dQ equals to PD times DC, according to rule number 2. AD is 1. Here, dQ is 1 plus 2, that is 3. PD is equal to 5 units. We already found out in the first method, and also OB is equal to 5 units according to the first method. This is the missing line segment. So here we found out that 3 equals to square root of 5 times DC. We divided this equation by square root of 5 and we found out that DC equals to 3 over square root of 5 units. Here DC equals to 3 over square root of 5 units, and we implemented the Pythagoras theorem on the right blue triangle DCB. According to the Pythagoras theorem on the right blue triangle DCB, dB square equals to DC square plus CB square. dB square equals to DC square plus CB square. dB equals to square root of 5, so dB square is square root of 5 squared, that is 5. And it is equal to DC square. DC is 3 over square root of 5, so DC square is 9 over 5. Plus CB square, that is the missing 9 segment. So we found out 5 equals to 9 fifths plus CB square. We subtracted 9 fifths from this equation. We found out that 5 minus 9 fifths equals to CB square. We multiplied 5 by 5 and then we divided by 5 in order to have a common factor with this expression. So 25 minus 9 over 5 equals to CB square. We took 25 minus 9 is 16, so here we got that 16 over 5 equals to CB square. We took root out of this equation. We found out that CB equals to the square root of 16, that is 4, over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5, and we know that CD equals to 3 over square root of 5, and dB equals to square root of 5 units. Now it is very easy to find out the area of this right blue triangle DCB. The area of this right blue triangle DCB equals to the base of the triangle, that is CD, times the height of the base, that is CB, over 2. Again, the area of this right blue triangle BCD equals to the base of the triangle, that is CD, times the height of the base, that is CB, over 2. CD equals to 3 over square root of 5 units, and here CB equals to 4 over square root of 5 units, all divided by 2. In the numerator we have 3 times 4, that is 12, and square root of 5 times square root of 5 is 5, times 2. 12 over 2 is 6, so in the numerator we have 6, and in the denominator we left only with 5. So in conclusion, we found out that the area of the right blue triangle DCB equals to either 6 over 5 square units, so in terms of numbers, it is equal to 1.2 square units. We finished with the first method, then I presented to you how to find out the area of the blue right triangle DCB according to the second method. So here we've already found out that this angle equals to 90 degrees, AD equals to 1, DO equals to 1, according to the first method. And then we completed the quarter circle to a semicircle. We define the touching point of the extended BO, and the semicircle is P. So O is the center of the circle, P is the point of the semicircle itself, therefore PO is the radius of the semicircle, that is equal to 2 units. So PB is the diameter of the circle, according to what we already found out also in the first method. We extended side CD by a straight line, and according to the first method, when we extend side CD by a straight line, it must pass for point P, it must touch point P. Okay, then according to the first method, this angle equals to 90 degrees. dP equals to square root of 5 units. According to the first method, dB also equals to square root of 5 units according to the first method. Angle DPO equals to theta according to our definition. This angle equals to 90 degrees, so in order to complete the sum of the angles on this right triangle POD to 180 degrees, this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. Okay, likewise, in the right big triangle BCP, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta. Here we put that the right triangle POD is similar to the right triangle PCB. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles, so this angle equals to itself. So we actually found out all three angles on the right triangle PCB can go into all three angles on the right triangle POB, therefore those two right triangles can go into each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB, that is equal to PO over PC. PD equals to square root of 5 units, PB equals to 4, DO equals to 1, and CB is the missing line segment. PO equals to 2, and PC equals to the square root of 5 plus DC. PC equals to the square root of 5 plus DC. So here we created the first equation. Those two expressions are equal to each other, so square root of 5 over 4 equals to 1 over CB. Because multiply this equation number 1, and we found out that square root of 5 times CB equals to 4. We divided this equation number 1 by square root of 5, and we found out that CB equals to 4 over square root of 5 units. Okay, CB equals to 4 over square root of 5 units. Then we implemented the Pythagoras theorem on this right blue triangle DCB. according to the Pythagoras theorem, dB squared equals to dc squared plus cb squared. dB squared equals to dc squared plus cb squared. dB is equal to 5, so dB squared is 5. This is the missing 9 seconds, so we leave this it is. Here, cb equals to 4 over square root of 5, so cb squared is 16 over 5. So in conclusion, we found out that 5 equals to dc squared plus 16 over 5. We subtracted 16 over 5 from this equation. We found out that 5 minus 16 over 5 equals to dc squared. We multiplied 5 by 25 and then we divided by multiplied 5 by 5 and we divided by 5 in order to overcome a factor with this expression. So 5 times 5 is 25. So we have here 25 minus 16 over 5. 25 minus 5 is 9. So in conclusion, we got that dc squared equals to 9 over 5. We took out of this equation and found out that dc equals to 3 over square root of 5 units. Here dc equals to 3 over square root of 5 units, and we already found out that cb equals to 4 over square root of 5 units, and db equals to square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area of the blue right triangle, triangle DCB equals to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. Again, the area of the blue right triangle equals to the base DC times the height of the base, that is CB, over 2. DC equals to 3 over square root of 5 units. CB equals to 4 over square root of 5 units, all divided by 2. In the numerator we have 3 times 4, that is 12. In the numerator we have 3 times 4, that is 12. In the denominator we have square root of 5 times square root of 5, that is 5, times 2. 12 over 2 is 6. So, and in the denominator we left only with 5. So in conclusion, we found out that the area of the blue right triangle DCB equals to either 6 over 5 units, or in terms of numbers, it is equal to 1.2 square units. Actually, here in the first method, I forgot to say that we get PD according to the Pythagoras theorem. We know that DO equals to 1, BO equals to 2, therefore the hypotenuse will be equal to square root of 5 according to the Pythagoras theorem. Here also, in the right triangle DOB, one side is DO equals to 1, OB equals to 2, therefore the hypotenuse OB according to the Pythagoras theorem will be square root of 5 units. Okay? So, thank you very much.